Thank you, Jan, and I'm Leonel Romero, and I'm going to talk about wave dissipation, spectral ranges, and energy balance. I'd like to thank the organizers for giving me this slot. Thanks to Fabrice, and thanks for Fabrice for coming up with a great title. And talking after Mark now is like, oh man, there's so much to think about. There's so much that maybe we can work together and improve these dissipation models. Okay, so let's get started. So the governing equations for the deep water waves is a radiative transfer equation with wind input, wave-wave interaction, and dissipation. And the dissipation includes two sources of dissipation. It's going to be the breaking contribution, but there's also a background contribution to dissipate the swell. In this talk, I'm going to be using the definition of, so do I see a pointer? I don't see a pointer. There it is. Yeah. Integrating my spectrum with kd, kd theta, you recover the variance. Many people try to absorb that k, that's the Jacobian, to go from Cartesian to polar. I always keep track of that k. It's just an annoyance. I've been doing it for 20 years. I'm probably going to start absorbing it so I don't have to keep track of k. If the units don't make sense, just keep in mind there's always a k somewhere there. And yeah, so there's wave breaking and non-breaking dissipation. So let's talk a little bit about the spectral ranges. If we integrate our spectrum in azimuth, we get two main ranges, two power laws. You get the k to the minus 2.5. And in there, the main balance is assumed to be between wind input, wave-wave interactions, and dissipation. Moving into higher wave numbers, the spectral slope changes to k to the minus 3. And there, the primary balance, depending on how big the parameterization of the wind input is going to be, is primarily between wind input and dissipation. So it's assumed that the wave-wave interactions are smaller, but they're still significant. And I'm introducing here, though there's weird symbols, this should be capital B, the spectral saturation. So it's a measure of the mean square slope locally within the spectrum if you assume self-similar wave groups. And that parameter has been used extensively to parameterize breaking in the field. So let's start with some historical context. One of the earliest parameterizations was introduced by Hasselmann and used by the WAM group. It was quasi-linear with a non-dimensional dissipation factor that is spectral, it's isotropic, and it has some parametric dependence on wave steepness based on integrated parameters, mean wave period, mid wave number, and significant wave height. And that one implicitly accounted for both breaking and non-breaking dissipation and was tuned to basically maintain the energy balance. There was no observations that went into constraining that term. Moving on, then Banner and colleagues showed that breaking probability was strongly dependent on the spectral saturation. Above a certain threshold of the saturations, the wave will break, and so he showed, and in those two studies, one was from dominant waves, and then it was extended to multi-scale analysis with the saturation, and show a pretty good relationship for this breaking probability in terms of the saturation. And that motivated the development of new parameterizations, and at that time became clear that you had to separate the breaking contribution of the dissipation to the non-breaking, which is the swell dissipation. If you don't do that, if you only account for the breaking, at some point you don't match the empirical fetch relationships. And the non-breaking contribution at the time, one solution was to use reverting back to Hasselmann type of dissipation. So now the modern spectral parametrizations of breaking, we have the developed by Ardois, Rogers et al., Zeiger, Liu, and Philippot. They all share two main things. They are strongly nonlinear dependence on the spectral saturation. They also have a cumulative term to account for long wave, short wave modulations. And we should be thankful because they can do a pretty good job at reproducing HS, TP, and other spectral metrics. But there has been a systematic bias in reproducing the observed directional spreading. So motivated by that, I worked on an alternative dissipation function that could fix that bias. But I also wanted to construct a breaking parametrization that we could directly do it in the framework of Phillips's lambda of C, which is a rational framework that allows us to relate several processes happening at the ocean surface. So it's a rather convenient and rational framework. So a lot of people, a few studies introduced this lambda of C yesterday. So this is the length of breaking crest moving with velocity C to dc. And the different moments you can relate to different processes happening. First moment is related to the breaking rate at a given point. The second moment you can relate to white gap coverage. Third moment you can relate it to the air entrainment. Fourth moment is momentum flux, and the fifth moment is related to the energy dissipation. So it's a rather convenient framework, and you can estimate it from video imagery, either from visible or infrared. All right, so here's how the sausage is made. The breaking parameterization is in terms of this lambda of C, and again, keep in mind that we're going to need the fifth moment and this little b, which is the breaking intensity. But let's start with the lambda of C model. So it has three components. One that comes from Gaussian statistics scaling as a function of the spectral saturation. We have another term, which is the modulation transfer function type term. This is the equivalent of the cumulative due to long wave, short wave interactions. And out of the need to balance the wind input, there's an additional term, direct modulation by the wind, but that's really out of necessity to maintain my level of saturation consistent with the observations. And for the modulation term, long wave, short wave modulation, I took some of the ideas from Donnellan in 2001 and on other ideas that Fabrice and some of the people in his lab have put together. And it depends on the cumulative mean square slope. And in this case, it depends also on a mean wave velocity weighted by the longer dominant waves. So that was the initial way it was framed. The actual details of this actual function are different between Donnellan, Guimares, Peru, and in this case, mine. If you compare mine to Donnellan's was even more nonlinear because he needed to balance the wind input without this additional term at the end. The one that Fabrice had explored wasn't as nonlinear as mine, was slightly lower in terms of nonlinearity. But the whole point is that this cosine term makes the dissipation narrower, and narrower than the spectrum, which basically allows the wave-wave interactions to put energy at wide angles and improves the spreading of the spectrum relatively well. for the last factor to balance the wind, so it depends on where your saturation level begins, and there's many ways of doing that. You could do it geometrically. People have balanced the wind also with highly nonlinear functions of the saturation. I decided to go with a wind speed dependence, which has been an annoyance since the beginning. Really, the advantage of that is that it makes things rather smooth. If I start playing with a high power of the saturation, like Banner has done, I begin to get like funny behaviors, kind of like what Fabrice showed yesterday. So I didn't really want that. So for now, we're still having a little dependence within the saturation range on friction velocity, and that's something we need to move away from. We don't want to have any wind dependence in a spectral dissipation function. But just keep that in mind, that caveat there. That's not the importance of this talk. This talk is really the importance of what's the effect of an anisotropic dissipation on improving the directional spectrum, which I think we all need to move towards in the future. All right. So once we have this model of lambda, we combine that with another parametrization that I developed by closing the energy balance. We had measurements of the lambda of C distribution. We modeled the spectral dissipation by closing the energy balance, by having measurements at different fetches, measure the friction velocities. So we were able to come up with indirect estimates of this spectral strength, and we fitted a model that came from a scaling from laboratory experiments for plunging waves, and we formulated it in terms of the saturation above a certain threshold. And the values from that model of the intensity of breaking is consistent with the model by Chris Zappa that was shown yesterday. Now, like the usual, you have to tune your model so you can match the fetch relationships. That's the first thing you have to do. Then you also have to worry about keeping track so many spectral parameters. You have to get the equilibrium range right. You have to get the saturation level right. I also constrained it so I could reproduce the observed lambda of C distributions in the field. And then comes the spreading. So how did I do that? So first, here is an example of idealized solutions with DIA and the exact wave-wave resonant interactions. I've been using the WRT, Webb Ratio Tracy code. And so the dashed lines are the DIA, the solids are the WRTs. This is the 1D spectrum. You develop your K to the minus 2.5 relatively well, followed into a saturation level. If you scale that by K to the third, you essentially rotate it. Now your K to the minus 3 is horizontal. And we're matching, roughly speaking, matching the ratio equilibrium range level and the saturation level observed with the LiDAR data by Luke and myself in the Gulf of Tehuantepec. One of the things that I was rather excited about is that Gaussian scaling factor, depending on the spectral saturation, allowed the lambda of C distribution model to reproduce a scaling that was found in the field by Sutherland and Melville. So here I'm showing you the model lambda of C distributions on the left. On the right are the lambda measured in the field. And one of the nice features is that they were able to collapse those data by using significant wave height, peak period, and friction velocity. And if I scale my model lambda of C's, I also get it to collapse relatively well along the same line. But notice that there is a roll-off here, slightly faster, and that has to do with how the wind input is acting. So depending on the wind input function, the shape of the lambda back out here would be different. Now, one of the advantages is that we have lambda of C. We can then compute different moments. We can estimate different breaking parameters. For example, the white cap coverage as a function of wind speed. You have few tuning knobs, which is like the duration of breaking. We assume that is proportional to the period of the waves themselves with a proportional factor. And so here's the whitecap coverage, a function of wind speed compared with observations, including Adrian's data, Sophia Brommer, and other 2 studies. And the next figure does not show, something went wrong. There was a submesoscale front that we captured during an experiment of Northern California. There was a lot of braking on one side of the front, little braking on the other, and there was more braking right along the front. And this is a classic submesoscale dynamics. You have surface convergence and a lot of horizontal shear. And that gave rise to this enhancement of braking along the front, but also more braking on one side, less braking on the other. And I'm sure someone else will show similar images later this afternoon, so just trust me, that's how it looks like. And so now we have an opportunity to try to model those situations. If you have a high resolution model with some mesoscale dynamics in it, and we can then force a wave model and maybe take a look at the modulation of braking by these sort of currents. And so I've started doing some of that work. And so here's an example. This is, you have the wind input, the wind forcing, sea surface temperature. There's a lot of cold filaments. Those are classic submesoscale dynamics. And you have, this is the mean currents. You can see a lot of gradients. HS varies around 30%. That's very typical in this submesoscale regime. And the surface currents, vorticities, pretty large vorticities, and surface convergences along these cold filaments, where you have a lot of downwelling. So now we're able to compute, for example, the modulation of gas transfer coefficients along these fronts due to wave current interactions. So these wave current interactions affect the braking rates, which then in turn we can model the gas transfer. And that's using the framework of Deca and Melville. And what we find is that that K gas transfer coefficient increases by a factor of 50% along these submesoscale cold filaments where you have a lot of downwelling. Now the question is that going to matter to the flux? That's still something I'm trying to work on. I think the answer is that you need areas where these features are persistent because they change rather rapidly. Now, going back to the parametrization and its impact on the spreading, which is the main point of this talk. Here I'm showing you the results from these idealized solutions. So on the left is the spreading as a function of scale for the DIA. The middle panel is this exact, using the exact wave-wave resonant interactions. And on the right is observations with LiDAR data in the Gulf of Tehuantepec. That was part of my PhD with Ken Melville. And we are able to improve the significant bias of the standard ST4 and ST6. And I'm going to show you a one-to-one comparison in a little bit, but just as a first glance, he's doing a good job at reproducing the data. Notice that this LiDAR data, it was what we were using back then. It was limited to 20-meter wavelengths or longer, so we don't have a lot of the data going into higher wave numbers. And this is the data that I use for tuning my parametrization. So just keep that in mind. Now, the other important aspect of this directional spreading is the directional distribution itself. We know that the spectrum is bimodal once you go from higher to higher frequencies or lower frequencies at the spectral peak. And Ian Young put out this way of visualizing it. So if you normalize your spectrum by the maxima for every K or frequency, you pick up these very nice bimodal structures. And this is from his paper. He was doing an array, spatial temporal measurements. And I was just reviewing it the last couple of days. And I noticed that in that paper, he already mentions that once you get into the high frequencies, you reach bimodalities approaching plus or minus 100 plus or minus 90 degrees. So you are getting into the regime of some of the stuff that Mark presented today. And of course, ST4 and ST6 are unable to reproduce that because their bimodality is not as broad. And if I show you, this is what the bimodality that comes out with my breaking parametrization. So you have very enhanced bimodality reaching about plus or minus 90 degrees at high wave numbers. Now, if you compare that, so it's DIA on the top, WRT in the bottom. If you compare that with ST4 and ST6, you clearly see that they don't get as broad, neither of them, as you can see on the left-hand side with the narrow dissipation function. So it's pretty clear. Now, yeah.
Which is the cause of bimodality? Why do we have bimodality?
It's from so you have the forward energy transfer and the inverse energy transfer by the wave-wave interactions. So it's part of the forward energy transfer.
But the anisotropic dissipation is very important also to get it right. So dissipation is important by modality.
But you can get bimodality without any dissipation, right?
Yes. But then this part is not as low. So the amplitude of the lobes relative to the center is not as high. And I'm going to show you a little more. So here is the same distributions. It's normalized distributions. Now, just to confuse you, I rotated them. Now theta is in the vertical, and now I'm in F. I was in K earlier. Now I'm in F. Just keep that in mind. So the three different breaking parametrizations, mine, everything got weird. Anyway, on the right-hand side, I'm showing the nonlinear energy transfers. These are the WRT, part of the solutions. And what you can see is rather interesting. So you can see that for ST4 and ST6, the magnitudes of the nonlinear transfers at high wave numbers are roughly a factor of 10 compared to those with the narrow dissipation. And this is a good example of the self-stabilizing effect of the wave-wave interactions that are trying to put the spectrum in their happy place. So if you were to perturb this bimodality, all of a sudden the magnitude of this SNL would increase to bring it back to what it likes. And that's something that Ian Young also talked about in earlier paper with Young and Van Bleder, and Recio has discussed some of that too. The interesting part is if you integrate the nonlinear transfers in azimuth, the magnitude for all three is about the same. So in 2D, you have a discrepancy of a factor of 10, but you have positives and negatives that they sort of cancel out. So in azimuth integrated, you end up with that. So all of them have about the same order of magnitude for the direct energy cascade, where you're taking energy from intermediate scales into the higher wave numbers. So this is really a reminder that we have to look at the energy balance in 2D, because in 1D, a lot of these things are going to be masked. Now let's continue talking about the sausage. So to characterize the bimodality, you can use two parameters. You can use the amplitude of the lobes, so it's how high they are relative to the center. And you can also use the separation in theta of those lobes. And so here are plotted as a function of the wave number. Separation is on the left, the magnitude is on the right, color-coded by the wave age. And in our LiDAR data from the Gulf of Tehuantepec, we found a pretty nice scaling that if you multiply those curves by the square root of the wave age, all the curves collapse along a single line. And that's what I used to constrain the dissipation. I did not constrain it to match plus or minus 90 degrees at very high wave numbers. I only constrained it at intermediate scales against this non-dimensional scaling. So I did tune that modulation transfer function, so I matched the non-dimensional, the scaled amplitude and lobe separations for the WRT. For the DIA, I can only do it for the lobe separation. The lobe amplitudes are too weak. You can never achieve the same amplitudes, but the angle separation is pretty good. And there are other implications for example, the mean square slopes. Here are the resolved mean square slopes out to 10 radians per meter as a function of wind speed compared to Cox and Monk. And this is for slick conditions. So you don't have the gravity capillary waves. We don't know exactly where the threshold is, so this is qualitative. But more interestingly, if you look at the downwind and crosswinds, again, comparing against Cox and Monk, there is qualitative agreement. And if you look at the ratio of the two, on the left is with the narrow breaking dissipation, middle is ST4, on the right is ST6. So clearly the crosswind mean square slope is much larger, consistent with Cox and Monk, whereas ST4 and ST6 is unable to reproduce that. So it's important for remote sensing, and as Fabrice mentioned, it's also important for the prediction of microseisms. So Fabrice did a very good job at explaining that, which I'm glad, that when you have waves going in opposite direction, you get a second order pressure signal at the bottom of the ocean. And Longett, Higgins, and others developed a framework for that. So it's the spectrum squared times this azimuthal overlap function, which is a function, it tells you how much energy is going in opposite directions. And on the left is the pressure that you would measure at the bottom at twice the frequency of the surface waves. And this overlap integral is defined over here. Now, in a very nice paper, Dunever et al. In 2012, they had pressure measurements at the bottom of the ocean in north of Hawaii. And they measure the left-hand side. They used a parametric model, an empirical model for the 1D spectrum, and they inverted what should be this overlap integral. They knew at the time that the models would not predict the spreading well, so they're like, okay, what spreading do I need, or what overlap integral do I need to match the observations at the bottom of the ocean? And that's what they did, and these are the solid lines on the right-hand side at different wind speeds, and again, everything got corrupted. I need to upload it again. And the dashed lines, they came up with a parametrization for this overlap integral that tells you how much energy there is at a given frequency or wave number in decibels. And if you compute that for solutions for ST4, ST6, and with my parametrization, we begin to approach that parametrization very well into the order 1 meter waves. And then Fabrice went a step further at doing direct comparisons between the measured pressure data at the bottom of the ocean compared to estimates with the right-hand side. And this is a correlation that he did with Alday last year. This is a function of the frequency and the correlation, so original ST4 is not correlated at high frequencies like he showed yesterday. Once you use my parametrization, you begin to get like 0.7 of correlation, and then he also used the Labrenov method optimized by Michel and his group, and you get an even better correlation if you use the exact wave-wave interactions. But Fabrice also showed that there were weird things happening every once in a while, and it had to do with the directionality of braking relative. So in conditions where you have rapidly rotating winds or misaligned long waves and the winds, there were funny behavior. And this is what happened for the original formulation. So imagine you have a 2D spectrum, you have the wind going to the east, you have a sudden shift in the wind, and the dissipation, remember that it had this constant direction weighted by the longer dominant waves. So what it did is that it would be dissipating at the higher wave numbers more in this direction than in the wind direction. So then at some point there was an imbalance, and then the tail of the spectrum will grow too rapidly to unrealistic levels. And it only happens very few times, but it does unrealistic stuff. So in one way, so when I finally saw Fabrice's results and I started thinking about it, okay, how can we address this? And a simple solution, which makes sense, is that this expression depends on the cumulative mean square slope. So we may as well use a direction that is weighted by the cumulative mean square slope. And so if I do that, then this is the cumulative mean square, the weighted direction by the cumulative mean square slope. So it's dependent on scale, and it would rotate as the winds rotate. And then this is what it was initially. This is after rotation. It was unrealistic saturation level. Now with this correction, our level of the saturation is still within observed levels. But of course, you could start arguing, do we need to use the cumulative mean square slope? Can we use something else? Fabrice has been saying, do we need a cumulative orbital velocity, for example? Maybe some of Mark's parameters that were introduced today. So there's a lot to be done, but I think that really the clear message is that the dissipation, if it's narrower, you allow the wave-wave interactions to do what they want to do and to give you a very good spreading and good bimodality. But there has to be some dissipation at high wave number to keep your lobes deep enough. So we started looking at direct comparisons between braking measurements and the energy spectrum. We took, Bernard Akawase is working in my lab. He's third-year PhD student and was interested in this problem. So he took existing data by Albice from the Aqua Alta platform and did some kinematics analysis from this stereo imagery. And here you have the directional spectrum computed from the WAS system. This is integrated in azimuth. And these are these lambda distributions that he's obtaining from this kinematic analysis of the video data. Now, if you normalize those 2D distributions, the way we've been doing that earlier in this talk, you get this extreme bimodality, as we said earlier, for the energy spectrum. This is rotated backwards. Low frequencies now are on the right. And then on the left, we have the lambda of C, which is much, much narrower compared to the spectrum. If we compute the spreading for the observations is super broad. The spreading for the lambda of C is very narrow, narrower than previous estimates, I have to say. Both Gemrek and Kleis were getting values of order 30%, reported little dependence on scale. So perhaps there are differences in the details of how it was computed. So I'm talking with Luke and to try to use some of the different methods for optical flow instead of PIV, see if that changes the results significantly. And on the right, I'm showing you a one-to-one comparison. This is the spreading from the model that I've been showing you before. And the spreading, so the energy spectrum is in blue. The spreading of the lambda of C model, it's in red, so it's roughly 35 degrees compared to around 20, up to 20 from the observed lambda of C. And again, this is comparisons with ST4 and ST6. So for the spectrum and the dissipation, they have, by definition, almost the same spreading spectrum and dissipation, which gives rise to the narrower spectrum. We're also funded to do more of this work with both visible and stereo imagery of Martha's Vineyard. So we're going to be deploying IR cameras and visible from the Air-Sea Interaction Tower, hopefully this fall. And we're also going to be doing subsurface TKE dissipation in collaboration with Alejandro Cifuentes. And so here's a comparison from Sutherland and Melville of this lambda of C with IR and with visible imagery. So once you start using IR imagery, you get a lot of more breaking at the shorter scales because those waves are not entraining air. So I'm interested in looking at these scales where the bimodality is really extreme and you have a lot of small-scale breakers. So I'm going to leave it at that. Where do we go from here? I think we clearly need a narrower dissipation function. We need a better theoretical framework to really improve these parametrizations. I also think that we need more measurements, and they can definitely help us keep improving these parametrizations. And we need to keep in mind the 2D source functions. Otherwise, a lot of the stuff gets masked away, and we're not going to get better. So I'm going to leave it at that, and I look forward to discussion this afternoon.